everyone, I'm Ming Hao. Now I'm a postdoc at the Carnegie Institution of Science, working with Dr. Anthony and Dr. McWater. I just graduated half years ago from University of New Mexico, got my PhD. My field is more specifically is mineral physics, but more study of the Earth's deep interior. Basically, my part is kind of help us to identify the eclogite material. That's a little different comparing to the normal metal. Normal metal is mostly peritite, but according to the geochemical observations, we should have some enriched reservoirs in the deep earth, which is totally different with normal metal. The most powerful tool for us to really understand the deep earth is the seismology. We need to use those seismic observation to help us constrain the structure in the deep earth. So we need to know the seismic properties for those eclogite materials so that we can identify where it is and how could those materials go to the deep earth and what happened maybe in the history, it's in the mental convection or just subduction or delamination. What happens? We need to identify those materials. So that's what my work is on. We measure the sound velocity for the eclogite parts to help those seismologists to constrain where they are and to understand what happened. Yeah, that's a part mostly for my PhD work, doing the sound velocity measurements to help people to identify those eclogite material in the deep earth, which is very important, basically a very important process when those enriched material go to the deep interiors. I think the biggest challenge is that for real measurements, we need to use very tiny little small sample, which at the dimension of 20 microns, very thin. We need to polish the sample to be very small and to kind of press those sample to high pressure and temperature conditions. And we need to, even at high pressure conditions, we need to make the crystal to be very good condition to be transparent, and no cleavage here, no fractures, and so that we can do very good experimental signals. That's sometimes we need to try a lot of times to really get a good sample at high pressure condition. 20 micron, even you may not see it with your eyes, draw your picture under microscope. do a painting under microscope like that. I think the coolest thing is that you can use two diamonds to press sample to reaching the really high pressure, exactly similar as the Earth deep interior, hundreds and thousands of meters deep. But right now we are mostly working on the mental wide reaction, which is when subduction is very important for geoscience, and when the material subduct down to the mantle, because of the high pressure and high temperature, and the hydrous layer will be melted, and then some melt or magma will go to the mantle and react with the mantle. Now my project is focused on this part, the reaction from the subduction going to the normal mantle. Yeah, we want to have some idea for the both seismic velocities and the electrical conductivity for those reactions in the mantle wedge parts. What's next? I think basically we are still looking at what really happened in these parts, and when we get some ideas what the mineral looks like and what the melt looks like, we can continue to do some ultrasonic measurements and do some multi-angle to generate those similar PT conditions to measure the sound velocity and the electrical conductivity, and we can compare it to the real observations. Then we can know what happened in this area. Good question. when I was at high school, actually, I starting to know like Earth have different layers, like crust, mantle, and core. That's very amazing because in the daily life we thought, okay, Earth is a sphere, but we only know, oh, there are some mountains, there are some seas. We didn't know in the deep interior actually there are still a lot of structures, which is really amazing, and I didn't know that. And during high school, we know, okay, so then what is that? Yeah, I think that's the idea. Yeah, everyone want to know what really happened, what it should be looks like, and then actually to like major in geology and typically like physics and or even high pressure field to really look at what we cannot see in our daily life. It's major like my former advisor, Dr. Jin Zhang. She really helps me a lot during my PhD research. Because basically, although I kind of did some, I already know some high pressure work when I was undergraduate, but I didn't have any master experience, so I directly from the undergraduate to the PhD. So my Dr. Jin Zhang really helps me a lot gradually, like becomes a good PhD student, like not only for the experimental skills, but also the background and the projects to gradually understand what's happening in the entire Earth and which parts we need to focus on and use which method we can solve the problem like gradually to. So all the mentorship, I really appreciate my former advisor, Dr. Jin Zhang. It's very important because mostly for undergraduates, you learn all different things like volcanology and seismology or something like mineralogy, all those basic things, but you do not have an entire idea what the Earth, the process should look like. You only know, oh, here have a there have a rock, you know the seismology, there's some wave. But you know how to like make everything together to understand the entire process in the Earth. It's really nice to have like different major people to discuss the similar problem, to have some idea from different abstract, from different fields, and that's really nice because sometimes, for example, I major in physics, but we need to borrow the observation from seismology. It's really important to know what they think, and how they understand the Earth, and how they understand our experiments. Kind of have a combination. That's really cool. Let me draw a subduction zone. That's what I like perfect. And maybe some delineation parts here. That's the delineation part from the continental crust, and here is the subduction zone. And here is our eclogite layer here. Yeah, and also maybe this part. I mean, you have some earthquake here. Go through it. And then I'm just having to consider what happens when the sand will go through the eclogite parts.
Excellent. Cool. Thank you.